Hi guys. So today we're going to be discussing Leetcode question 338 counting bits. So the question is given an integer n, return an array answer of length n plus 1 such that for each I between 0 to n both inclusive, answer I is the number of ones in the binary representation of I. So what it basically says is if this is the input n equals to 5. So the returned array, the output of your code should be something like this. It should be an array of max index 5, so basically length 5 plus 1, and they should hold the number of ones in the binary representation of the index. So the binary representation of index 0 is 0, number of ones in it is 0, so we write 0. The binary representation of 1 is 1, number of ones 1. Binary representation of 2 is 1 0, the number of ones in it is 1. The binary representation of 3 1 0 1, sorry, this is just 1 1. Binary representation of 3 is 1 1, the number of ones in it is 1 2. For 4 we have binary representation 1 0 0, number of ones is 1, and for 5 we have 1 0 1, the binary representation is 2. So this is the output that should be received. So how can we code this? The first approach is very straightforward, which is using the most obvious approach is basically traversing the array and calculating binary representation of every element. So basically what we do in that scenario is traverse over the array. So basically go over all the array in a for loop, and for every element, let's say the element is num. So for nums, as long as it's greater than 0, what we do is we create a temp array, let's say a binary array, whose index we keep incrementing, index plus plus after every iteration. This is basically to hold the binary representation of it. So num percentage 2 equals to this, and num is equals to num divided by 2. This is essentially setting the bit. So let's take an example. So let's say if we have n equals to 5, if let's say we're working on nums equals to 5, right? So this will result in an array where the first index, let's say index equals to 0 right now. So num percentage 2, this will be filled by num percentage 2. What is 5 percentage 2? That is 1, sorry. So this would be the bit of 5. Then num was 5, now is divided by 2. So integer division by 2, this results in 2. 2 percentage 2, 2 modulo 2, that gives us 0. So this is the next bit of the 5 representation. So divide this by 2, this gives us 1. So 1 modulo 2 is 1 again at the index 2. So this is complete binary representation of 5, because num has become now 0 after division by 2, and that is when we stop, and this gives us the binary representation of 5. So this is a log n approach, and since we are going over all the array elements, so this becomes an n log n approach, this complete algorithm. So can we do any better than this? Can we do it in an O of n solution? So this is where the dynamic programming comes into picture. DP approach. The time complexity for this is time complexity is O of n. So what is the approach? The approach is simply just using previous values calculated to get the new values. So previous values, the number of ones computed for earlier numbers, to get the number of ones in the new number. So let's say we have a table where the first column is the number, the second column is the binary representation of that number, and the third column is count of ones in that binary representation. All right. So let's say the number is 1, sorry, let's start with 0. 0 1 2 3 4 5 6 7 8 9. All right. So the binary representation of 0, what is it? 0, right? Binary representation of 1 1. 2, binary representation of this is, binary representation of 4 is 1 0 0, 1 0 1, 1 1 0, 1 1 1, 1 0 0 0, 1 0 0 1, and so on and so forth. What is the count of ones in it? 0, right? The count of ones in one, binary representation of 1 is this, binary representation of 2 is 1 0, the number of ones in it is 1, the number of ones here is 2, the number of ones here is 1, the number of ones here is 2, then again number of ones is 2, now here its number of ones is 3, this again is 1, this again is 2, and so on and so forth for the numbers. So can we find any pattern in between these things? So first thing you need to notice is 2 raised to power, so the 1 can be written as 2 raised to power 0, 2 can be written as 2 raised to power 1, 4 can be written as 2 raised to power 2, 8 can be written as 2 raised to power 3, and so on and so forth. So every power of 2 power of 2's have how many ones in it? Just 1 counts, right? Just 1. See, notice this is just 1, 2 raised to power 1, which is 2, with again this is the number of ones in it is 1, the number of ones in the binary representation of 4 is 1, the number of ones in the binary representation of 8 is again 1, and so on and so forth. So this is one thing that we can clearly see. The other thing that we can see is, so this is 3, right? So we can always write 3 as, let's say, what was the last power of 2 but just before it? That was 2, right? 2 raised to power 1. And what is the remaining amount, which is 3 raised to power minus 2? So this is 2 plus 1 essentially, which is 3, right? So what we do here is we add the binary the number of ones in the binary representation of 2 and the number of ones in the binary representation of 3 minus 2. This gives us the number of ones in the binary representation of 3. So let's check this. So on this side we have binary representation of 3 1 1 and the number of ones in it is 2, right? So this can be written ones in last power of 2 plus ones in, what is the value, current value, let's say val, minus last power of 2, right? So this is what we discussed, right? So the number of ones in the last power of 2 is, we can check that from here, which is 2. So this is just 1. Number of ones in the last power of 2 will always be 1, since we discussed here power of 2's have 1 count, right? So this would always be 1, this would always be 1, plus ones in what? 3 minus 2. So 3 minus 2 is 1. So how many ones do we have in 1? Just 1. So this becomes 1 plus 1 equals to 2, which is exactly what we have here. Alright, so I'll be erasing this for now. So this is the actual formula. So now let's verify this for the next iteration. So this was 2 here. So let's say now we are working with 5, n equals to 5. So 5 can be written as, what was the last power of 2? 4, earliest power of 2 just before this number, 4 plus 5 minus 4, right? So this is essentially 4 plus 1, which is equals to 5. So the number of ones, since this is 4 plus 5 minus 4, right? Not this, but the 5 here can be written as this. So what are the number of ones? Sorry, ones in 4, the number 4 that we are working with here, plus ones in 4 minus 5. I'll just write this in a different color for you to easily visualize. So this is 4 and this is 5 minus 4, right? So what are the number of ones in 4? This is 4. And what are the number of ones in 5 minus 4? So this would be ones in 4. Since it's a power of 2, this would be 1. And ones in 5 minus 4, ones in 1, we can always check that because we have already computed that. So this can be computed from here, which is 1. So this is again 2. And this is equal to this. So this has been also verified. Let's do one last verification. So let's check for 7. So when n equals to 7, right, 7 can be written as, what was the last power of 2? 4 plus 7 minus 4, 3. So 4 plus 3 is 7. So this is ones in 4 plus ones in 7 minus 4, right? So how many ones do we have in 4 since it's a power of 2? So 1 plus ones in 7 minus 4. So where's 7 minus 4? That is 3, right? So this would go back to here since we've already computed this. So this is 2. So this gives us 1 plus 2 equals to 3, which is exactly what is here. So this verifies our formula. So now that we have discussed this through the dry run approach, what the actual formula is, let's write the heart of the algorithm for the dynamic programming. So the heart of the algorithm is, there are 3 parts of heart of the algorithm: verbal description of sub problems. In this case it would be S of k is equals to, S is our dynamic programming array, so number of ones in binary representation of k. So this would be S of k. What is the second part of heart of the algorithm? Mathematic recurrence, right? So we write first for the base case. What would be the base case in here? The number of ones in the binary representation of 0 is 0. The number of ones in binary representation of 1 is 1. The number of binary representation is 2 is 2, because these are the base values that we use to compute further values. If this is for the base case, what is for the general case? The general case would be, since we discussed that if k is a power of 2, or we can say k is essentially last power of 2 star 2, basically a power of 2, right? This is to keep track of what was the last power of 2 used. So any power of 2, proper power of 2, would always have number of ones in it as 1, right? And you just update it to the new power of 2 for further calculations. Since k is the new power, so we update this value. Also, if k is not a power of 2, it's like a random number, it's like a different number, let's say 3, 5, 7. So in that case, you'll first create a variable difference, which will store the value, the current integer index, and subtract it from the last power of 2. Basically get the difference of how much it is different from the last power of 2. And then use this formula, 1 plus S of difference. As per what we had discussed, notice this is ones in last power of 2, and this is ones in current val minus last power of 2. So this is the same formula that we're using. So once the general case is also defined, the last part of the heart of the algorithm, what is that? Where is the solution found? Since our objective is to return the complete array that represents the number of ones in the indices, right, at their corresponding positions. So in this case the solution would be the complete array. So you just compute the array and return it. So this would be our answer. So this is our solution, and this is our complete heart of the algorithm for this, for counting bits approach using dynamic programming approach. I hope you guys found this video helpful, and I hope you understood the heart of the algorithm as well as why we did that. How did we come up with the formula using this dry run of this approach. I hope you guys found this video helpful. The link for the GitHub code for this question would be attached in the comment section, in the description below, along with the link to the original Leetcode question. I hope you guys found this video helpful. Thank you and have a nice day.